So thank you. Coming back to the heat transfer through a composite slab. So far we have finished the conduction heat transfer through layers of slab, considering the series resistance or considering sometimes parallel heat flow and series heat flow, etc. And now we will see what is thermal contact resistance. See, normally when two dissimilar materials are joined together, however smoothly we finish their surfaces, still at micro level projections exist. So these two materials will not sit together perfectly and they land on their projections, leaving some gap in between the two surfaces. And this void space between the two contact surfaces is usually filled with air or the surrounding fluid, and thereby these entrapped gases between the two surfaces arrest the conduction heat transfer, because the conductivity of a gas is much less than the solids. For example, look at this figure. Material 1 and material 2 are joined together, but at the micro level, if you see, you have the projections, so the material will not come in complete contact with the other material, so these void spaces are filled with air. And the thickness of this gap between material 1 and material 2 will be in microns, negligibly small, but still it accounts for a lot of resistance for heat transfer because of the poor conductivity of the gases. So that resistance offered at the interface of two dissimilar materials is known as thermal contact resistance. So whenever there is a resistance for heat transfer, obviously there happens a temperature drop. We have seen earlier also, if the resistance is 0, which is an ideal case where thermal conductivity tends to infinity and the temperature gradient will become 0. Here at this interface the resistance is maximum, because the formula for resistance is del x by Ka. That del x, the thickness is very small and the conductivity is very low. So therefore the resistance offered for heat transfer is very high at this point. So it is subjected to a maximum temperature gradient, almost vertical line. The gap between these two at the interface level is in microns. So the temperature drop is expressed as a vertical line. If you neglect the thermal contact resistance, that is the distance between these two materials, Tc1 will be equal to Tc2, because you are neglecting the material 2. In between these two you have another resistance, which is because of the air gap or the fluid which occupies the void spaces between the two surfaces. So hence there are three resistances. One is conduction resistance of material 1, and the second one is the thermal contact resistance, and the third one is conduction resistance offered by material 2. So therefore, Q is equal to delta T by R total, T1 minus T2, and between these 2 points, T1 and T2, the total resistance is R conduction of the first material and R thermal contact resistance and conduction resistance of the second material. So the expression for Q is T1 minus T2 by R1 plus R contact resistance plus R contact 2. Because the same heat is flowing through all these three layers as per law of conservation of energy, whatever amount of heat passes through material 1 shall pass through the gap and again shall pass through the material 2. So hence you can also write the equation for Q as Tc1 minus Tc2, that is the temperature across this interface, divided by only that resistance, that is called thermal contact resistance. The reciprocal of thermal contact resistance is known as thermal contact conductance and is given in the units watt per Kelvin. So we can say that when two dissimilar materials are joined together, at the joint there is a possibility for entrapped gases, and these gases being poor conductors when compared to the solid materials, it offers more resistance for heat transfer. Because they are offering more resistance, there is a drastic temperature drop across the layer, and that resistance offered at the interface of two different materials is known as thermal contact resistance. Now coming to the drop in temperature due to this thermal contact resistance from Tc1 to Tc2 is in negligible thickness and hence can be treated as a sudden drop. And thermal contact resistance depends on the surface roughness, interface pressure, and type of the material. For example, if the materials are surfaces are not properly finished, imagine rough surfaces. So when you place one over the other, the gap between the two materials will be large, and hence they offer more amount of thermal contact resistance. Similarly, to avoid this thermal contact resistance, if you attach one to the other by applying large amount of pressure, then interlocking of the projections will take place, and thereby avoiding voids between the two surfaces, or it will expel the gases in the space, thereby thermal contact resistance decreases. And of course the type of material, soft materials, very easily they interlock with one another at the interface, so the contact resistance will be less. And similarly, if you assemble two different materials under vacuum condition, that will also lead to a reduction in thermal contact resistance. Similarly, when you are joining two different materials, to avoid this thermal contact resistance, in between the two surfaces, you can think of adding some soft material or adding some greases, like silicon grease substances like that, which will fill the gap and have better conductivity than the air. So these are all certain techniques to reduce the thermal contact resistance between the surfaces. One common example for this thermal contact resistance where we see in most of our daily lives is copper bottom vessels. If you look at the copper bottom vessel is generally made up of stainless steel, and for better heat transfer, a copper bottom is attached at the end. So if that copper bottom is not properly attached to the base of the vessel, there exists a void space which will be occupied by the air and offers more amount of resistance for heat transfer, and hence the overall resistance will increase. Under such circumstances, instead of a copper bottom increasing the rate of heat transfer, due to this existence of thermal contact resistance, it will reduce the rate of heat transfer and leads to more consumption of fuel for the cooking process. So that is why when you buy a copper bottom vessel, you have to go for a branded one which is assembled in a factory, taking care of all these factors which we have discussed with reference to the thermal contact resistance. Now let us have a problem. A stainless steel plate of diameter 15 centimeters and thickness 3 mm and a copper plate of same diameter but thickness 5 mm are pressed together. The overall temperature difference across the plates, that is from T1 to T2, is given as 170 degrees. At the interface, there exists a thermal contact conductance of 3000 watt per meter square Kelvin. So this is the conductance, so reciprocal of it will be the resistance. Calculate the heat transfer and temperature difference at the interface. One-dimensional conduction, of course, without internal heat generation through a slab under steady state. These are all the assumptions we are taking. Thermal conductivity is constant, it's not a function of temperature. All those things are not presented here, but those are all the assumptions while taking the solution of this problem. So this is a problem related to a composite slab because you have different materials, steel and copper, attached together. And moreover, at the interface, he says there is a thermal contact conductance, which indicates you have to consider the resistance at the interface also. So altogether, there are 3 resistances for the heat to flow from one phase to the other phase. Steel, resistance offered by the steel material, and resistance at the contact, and resistance offered by the copper material. The resistance of the steel is given by del X1 by K1A1. The unit is degrees centigrade per watt. And the conduction resistance of copper is del X2 by K2A2. That is also degrees centigrade per watt. Hence, the thermal contact resistance should be also in degrees centigrade per watt if you want to add these 3 resistances. But the conductance is given in watt per meter square Kelvin. So resistance becomes Kelvin meter square per watt. So that meter square is addition, which we have to remove by dividing with area. It is the total thing is given. Per area, you have to divide. Interface contact resistance is per unit area 1 by 3000 by A1, where A1 is the area normal to the direction of heat flow. So a note is put here. The conductance is given per unit area, hence total conductance is 3000 into area. So therefore interface or thermal contact resistance is 1 by total conductance 3000 into area. Now hence R total equal to R steel plus R contact resistance plus R copper. Since it is a slab, the area is the same, A1 equal to A2 equal to, and all these plates are circular plates, 5 by 4 d square, which is 1.76 in 10 power minus 2 meter square, and R total is del X by K1 A1 and 1 by conductance del X2 5 mm by K2 A2, and the R total is 26.593 into 10 power minus 3 Kelvin per watt. Now once you know R total, you can get the heat transfer across the plates, delta T by R total, which is equal to 6.39 kilowatts. Now another question asked here is, determine the temperature difference across the interface. The amount of Q we have found is 6.39 kilowatts, and that 6.39 kilowatts will pass steel against the resistance offered by the steel. The same amount has to pass through the copper plate against the resistance offered by the copper, and the same amount will also pass through the interface resistance. Therefore, you can write the equation for Q as Tc1 minus Tc2 divided by thermal contact resistance. Therefore, Tc1 minus Tc2 equal to Q into thermal contact resistance. Q is 6.39 into 10Q, and thermal contact resistance is 1 by 3000 into area. 3000 into area. So you will get 120.5 degrees centigrade. So the temperature drop at the interface is 120 degrees centigrade roughly. What will be this value if we neglect the contact resistance? Suppose we neglect the thermal contact resistance, then the temperature drop will become 0. See, due to the contact resistance, maximum amount of temperature drops at that point, which is a disadvantageous thing. So that is about the thermal contact resistance when two dissimilar materials are joined together. The problem will be there even for similar materials also, but normally when we have similar materials, we don't go for joining them. We can even have an integral one. So what are the points with reference to this thermal contact resistance? You can minimize this thermal contact resistance by applying a thermal grease like silicone oil, or replacing air with better conducting gas such as hydrogen or helium. That means assembling it in the cloud of hydrogen or helium gas so that the void space is filled with hydrogen or helium rather than air, which is having better thermal conductivity. Inserting soft materials between the two parent materials such as tin, copper, silver, nickel or aluminum foils, so that the white space is filled with these better thermal conducting materials, and maintaining smooth surfaces so that the gap will be minimum and thickness of the film becomes very small. So when the thickness of the film is small, the resistance also becomes small. And then assembling the two plates at high pressure so that the projections of one body will pierce into the other and interlocking of surfaces will occur, expelling the air in the void space, and assembling under high vacuum conditions. So when these precautions are taken, the thermal contact resistance can become minimum. So that's all about the composite walls and thermal contact resistance. Now let us have some review questions. Already 16 review questions are presented in the last sessions, and the answers are also given in the previous sessions. Now let us take a look at the questions from 17 to 26. Mostly all these questions are based on conceptual understanding. So consider a one-dimensional heat conduction through a cylindrical rod. What is the heat transfer area we have to consider if the lateral surfaces of the rod are insulated, and if the top and bottom surface of the rod are insulated? The second question, consider heat conduction through a wall of thickness L and area A. Under what conditions the temperature distribution in the wall will be a straight line? Is a micro oven viewed as a conventional oven with zero convection resistance or not? Consider a window glass consisting of two 4 mm thick glass sheets pressed tightly against each other. If we replace these two 4 mm thick glass sheets with a single 8 mm glass sheet, what will happen to the rate of heat transfer? Imagine steady state heat transfer through the wall of a room in winter. The heat transfer coefficient at the outer surface of the wall is 3 times that of inner surface. So on which surface of the wall you think the temperature will be closer to the surrounding air temperature? Heat transfer coefficient. Next, the bottom of a pan is made up of aluminum layer of 4 mm thick. Now this is made into two 2 mm thick layers, and between the two layers a 3 mm thick copper layer is sandwiched. So it is also made a composite layer. One 2 mm aluminum, and then 3 mm copper, and then 3 mm. So due to introduction of this copper layer, will the heat transfer improves or not? Neglect the thermal contact resistance. Next, will the thermal contact resistance be greater for smooth or rough surfaces? Then a wall consists of two layers of insulation pressed against each other. Two layers of insulation. Do we need to consider thermal contact resistance at the interface or not? Next, consider two surfaces pressed against each other, and the air at the surface is interface is evacuated. Will the thermal contact resistance increase or decrease as a result? Next, can the thermal resistance concept be used for a solid cylinder or sphere in steady state operation? Explain. So try these answers from 17 to 26 questions. I will present the answers for these questions from 17 to 26 in my subsequent sessions. So again, I suggest you to give a vigorous reading to any one of these textbooks and do practice, otherwise it is very difficult to understand the problems. So only when you do, you will understand. It's simple logic. So related to these topics, whatever so far we have covered, I advise the students to take up some problems from these textbooks and try. You can send your queries to me or to the organizer so that we will immediately give you a reply to you. Thank you.